So now that you've seen the code, let's go ahead and talk about the good and bad of this thing. Why is it a problem? So the question is, if we were to run this code, what would the output be? What would be the consequence of running this code? And here's just an example of running the code. You could get different output on different platforms because all this stuff is fundamentally non-deterministic, so it's never quite clear what exactly you'll get as a problem. But what we're getting here is we're getting a Java null pointer exception when we're trying to remove something from the linked list, and that's because the thread has been, the state of the thing has been corrupted because of concurrent access to the state. And the reason why you'll get different behaviors is because there could be different implementations of the linked list in different versions of the JVM. And so in some cases, you could just get it to hang. In other cases, you get an exception. Whatever the case is, bad things happen. And the question is, why do bad things happen? And the reason that bad things are going to happen is because there's no protection in these hopefully to be critical sections where we're adding and removing something from the queue, from the underlying linked list, rather. And as a result, as the different threads do this, they're going to be corrupting the data structures. And in fact, the linked list documentation actually tries to tell us this. It tries to say, hey, this implementation of the linked list is in fact not synchronized. And so if you access the linked list and you modify the list, like adding and removing from it, it has to be synchronized externally. And we didn't do that. So obviously, bad things will happen. So concurrent programs in general are hard to develop and debug due to various inherent and accidental complexities. So you can end up with deadlock, where you have one thread holding a resource and then wanting another resource, and then another thread holding that resource and wanting the other resource. And so they end up with this thing called a circular embrace, so nobody ever gets a chance to run and do their job. There's also something called starvation, where you might have a lot of threads, and the higher priority threads always get access, and they're running, and they're getting their job done. And then you have some other thread that's a low priority thread that never gets a chance to run. So that's called starvation. You never get a chance to get your resource. Race conditions, which is where you have the sequence or the timing of the threads make a difference in terms of whether the program runs properly. Those are the problems we keep running into and all this stuff. And then tool limitations. So things, for example, if you don't have a debugger that works with multi-threading. Another big problem that you'll discover as you try to debug your programs is that the very act of debugging can cause the behavior to run in a slightly different way. So if you have a program that runs a certain way when you don't have the debugger set with the breakpoints and so on, you might get one output. And if you have race conditions, if you try running with the debugger, all of a sudden the timing will be different. So you might either get a different bug, you might get no bug, or it becomes very hard to replicate the code. That's sometimes called a Heisenberg bug, as it's sort of a joke, because it means that the very act of looking for the bug causes it to change. Some of these problems can be fixed by applying built-in monitor objects, in particular the race condition stuff. And that might also help with the Heisenberg bugs too. There's also other helpful techniques to think about when you design concurrent software. So if you take a look at this link, it gives you some good tips on how to write effective multi-threaded code. But multi-threading is sort of an inherently complicated thing to do. Okay, so that's basically the overview of the evaluation.